Next week on Tuesday, I'll be doing another recitation. That's going to be kind of a more exam review focused, but there is a topic or two that I'm not going to get to that he's going to be giving on Monday. So I might go over that as well. And then the following week, the quiz is on Wednesday, so I'll go over the material for that quiz on the Tuesday, the day prior. So I'll do that in that recitation. So you'll still get the full quiz prep for that one, but it'll be the day prior instead of about a week prior, so that I can still do the text review for exam 3. Okay, so last time we went over a few things. So just a quick reminder. So we went over subspaces. Remember, those were subsets that follow certain rules. We went over what a span is. We went over null spaces. And we went over ranges. And remember, for the null space, that's the set of all x element of Rn for an n by n matrix, such that Ax is 0, and the range was the set of all y element of Rm, such that Ax equals y. So two slightly different things. So this week, we're going to talk a little bit further. So we're going to talk a little bit first about what a spanning set is. So we talked about the span, and last week we focused on kind of an arithmetic relation where it was the set of x element R such that there's some relation between the elements of x. But this time we're going to talk more specifically about the sets. So this is what was introduced yesterday, I think, in that lecture. So if S is a subset of W with S equal to some set of vectors, then S spans W if every vector in W is a linear combination of the elements of S. Okay, so this is the same thing basically that we said yesterday, but now we're going to, instead of defining it as a relation, we're going to define them simply as just sets of vectors. So we'll kind of show that right here. So a couple examples. The first one is just the simple, does S equal U1, U2, U3, span a set of three-dimensional real numbers. So we have U1 equals 1, -1, 0. U2 is -2, 3, 1. U3 is 1, 2, 4. So then we have this problem, and if this set of vectors spans the three-dimensional space, that means that we should be able to create any vector in R3 from this group. So what that means that if we create our augmented matrix, and we have some A, B, C, then this guy must be consistent for all A, B, C elements of R. So if we do this real quick, and we break down the matrix, we get get rid of that second row so that we get add them together, 1, 3, and a plus b. And taking it one step further to get rid of this bottom 1, so we get it into echelon form, 0, 0, -2, 1, and this will be 0, 3, and then this will be 1. We'll get a plus b, and c minus a minus b. And we can see right now, so we don't have to go any further with this because we have it in echelon form. And we can see that this is going to be consistent for every element of, for every ABC element of R. So since it's consistent, we don't have any 0 row. They all will have a leading 1 in the reduced echelon form. We know that it's going to be consistent, so we know that S spans R3. That's just a quick example. One more. So let's say in the previous lecture, we found that, let's say the null space of A equals the set of all X element of R4, such that -2, -1, 1, 0 is X3 plus -3, 2, 0, 1, X4. I wrote this funny, but equals that X. So the 4, so X1, X2, X3, X4, just basic addition right there. So what this means, that this is the exact same as the span of the set with just -2, -1, 1, 0, and -3, 2, 0, 1. Because what the span is saying it's a set of any combination, and that's exactly what this is saying. So if we plug in any value for x3 and any value for x4, we create a linear combination, and that's exactly what this is saying. So this is saying any combination of these two vectors. So these are equivalent. So this is just our new way that we're talking about spans today. It's just in sets of vectors. And I've seen some of the quizzes have already shown answers in that format. So it looks like people are looking at the lectures in the book. Okay. So the basis, the next thing we'll talk about is a basis, or a minimal spanning set. Minimal spanning set is a term for it, but it's really more of a definition. What we're talking about here is basis is the official word for it. It's a linearly independent spanning set for W. So why is this important? So when we're looking at a linear independent set, that means it's going to have minimum number of vectors possible to span W. And this is good because we don't want to create redundancy. So we don't want to have 4 vectors define a space that could be defined with 3 vectors, because it's inefficient and it doesn't really accomplish our goals. So we'll talk quickly about a basis. So a few examples. So first, to start off, let's say we have, I'm going to go to the next page because the next 2 problems go together. So looking at the homework, we had 3.4.1. So 3.4.1 had a set of equations. So the set of the equations they have is x1 plus x2 minus x3 equals 0, and x2 minus x4 equals 0. And they want us to find a minimal spanning set or a basis. So in order to find this basis, we could do it two ways. So um, we can just solve directly for x1 and x2. So we can see that x1 equals x3 minus x4. And we can see that x2 equals x4. We could also, if we wanted to, we could do the quick system just to get it in reduced echelon form, because that's what we're used to. Notice that this is a homogeneous equation. So what we're really solving for here is the null space. So we're finding the null space of this matrix right here, and then, or this matrix, and then we're finding the span of that null space. So this is a really easy one. And we'll just get 0, -1, 1, and 0. So then both of these get us the same solution. And if we rewrite this, we know that x is going to be 1, 0, 1, 0, x3. -1, 1, 0, 1 times x4. So our basis is going to be the span of, or sorry, the basis will be the set itself. It's going to be 1, 0, 1, 0, and -1, 1, 0, 1. So this is the minimal spanning set. So this is the minimal set that we can create that will be, the span of this set will be the same as the span of the larger set. Does anybody have any questions right now on the basics of what the basis is? I'm going to do a few more examples, but I want to make sure that I've kind of explained the first part clearly. Back one page. So I was just saying here, so it's a basis is a linearly independent spanning set for W. So it's the minimum number of vectors possible to span W. Okay, so let's do another example. So this is going from the previous one, and it's asking if a couple of vectors are in the span of the set. So this is very similar to problems we did last time, and it's very similar to a problem that is on a quiz. But so we have this basis. We have to determine if two vectors are part of the basis. So the first one is 1, 1, 2, 1. And if we want to figure out if that's in the span, there are two ways to do it. We could solve for a consistency condition, and then we can ensure that it falls into the consistency condition, or we can just directly solve for the coefficients x1 and x2 to that we would multiply by each of these vectors to get it. And that's what we're going to do because that's easier in my opinion. So if we just draw out the augmented matrix, and we can solve this augmented matrix. We get 1, 0, -1, 1, 1, 1. And then over here, we're going to get 0, 1, 1 is 1. Sorry. Minus -1 is +1. And 2 minus 1 is 1. Okay, sorry. And then on the bottom we'll have 0, 1, 1. So we can quickly see that these two, we can just delete the bottom two rows. So we're going to get 1, 0, 0, 0. Then we're going to get 1, 1. And then these bottom two are gone. And if we add the second row to the first, we get 0 and 2. So we can see that 1, 1, 2, 1 is just going to be 1, 0, 1, 0 times 2 plus -1, 1, 0, 1 times 1. And if we look at that real quick, 2 minus 1 is 1, 0 plus 1 is 1, 2 plus 0 is 2, and 0 plus 1 is 1. So we're good to go. Similarly, we can check another one. So let's check x equals -1, 2, 3, 2. And in this case, if we do the same thing, I'm going to cheat real quick because I know that the first two columns are going to stay the exact same because I'm going to do the exact same matrix operations. I'm just going to draw those in there from above. And then I'll just make sure that I perform the same operations on this row. So 2, 3, 2. And then what we did here is we subtracted row 1 from row 3. So 3 minus -1 is 4. And then 2, 2, and -1 still. And then if I subtract row 2 from row 3 and 4, I end up with a 2 right here. And then on the top, I'll a 1. So the problem is this row right here. We can see that we have 0 equals 2, which it does not. So it's inconsistent. So we know that x is not an element of S, or W, sorry, because the basis is created for W. So S is not in the W that is defined by this basis. Okay. We'll do one more example on the basis before we move on to the dimension, nullity, and rank. So let's look at 3.4.23. Okay. So S is a set of 4 vectors. And I think the question is find a basis for this set. So let's find a basis. So if we create the augmented matrix, we're going to use a method. So the method we're going to use, I don't know if I've mentioned this yet. So we're going to set the equation equal to the 0 vector. And we're going to determine which columns are linearly dependent and which ones are linearly independent. And if we identify a linearly independent column, then the columns associated with a vector are going to be our minimal spanning set. So that might not make sense right now, but I'm going to go ahead and do this, and hopefully we'll be able to see. So if I do a couple of operations, so let's do 0, 1, 1, 1. And down here, we're going to have 0, -2, -2, 2, 0. So that bottom row goes away. And the top row, modified by this guy. So all we do is subtract 2 times that. So we'll get 0, 1, 3, 0. And if we look at this, we notice that we have linearly dependent vectors right here. So these are dependent, or free variables, sorry. It's linearly dependent, and we have free variables in these two spots. And here, we have unconstrained variables. So what we can do is, you notice that the first and second row, or first and second column, have unconstrained variables. That means that we can create a basis from the set of just those first two vectors that we started with. And obviously we're going to need more than one vector, because if we just have one, there's no way I can multiply 1, 2, 1 by a constant to get 2, 5, 0. And we can check this real quick by just looking at, looks like 1 plus the first vector plus the second vector is the third vector. And then 2 times the first vector, or 3 times the first vector minus the second vector is the fourth vector. So if we have 3 minus 2, it's 1. 6 minus 5 is 1, and 3 minus 0 is 3. So we can see that this is a basis. And then the reason that we can kind of skip that step and go straight from there to there, just to give you some rationale so you understand where it's coming from. We have from the matrix that x1 equals negative x3 minus 3 x4, and we have that x2 equals negative x3 plus x4. So if we set x3 equal to 1 and x4 equal to 0, then negative v1 minus v2 plus v3 equals 0, so that v3 equals v1 plus v2. So we can clearly see that from our matrix up here. Similarly, if x3 equals 0 and x4 equals 1, then negative 3v1 plus v2 plus v4 is going to equal 0, so that v4 is a linear combination of v1 and v2. So this is why, so we can get from here, and when you have free variables, you will always be able to show that the free variables are the vectors associated with those free variables are always going to be combinations of the unconstrained, or the, sorry, I'm messing up some terminology. So this is constrained, sorry. So the first and second are constrained variables. One or two of you are probably sitting there yelling at me. So those are constrained, and these are free. So when we have constrained variables, those columns are going to be associated with members of the spanning set. So that's a nice shortcut we can take to get to our solution. So that's a quick way to do it. It's not too complicated. Okay, any questions on the basics of what a basis is before I move on to the next topic? Okay, I'll go ahead and move on to dimension. So dimension is a pretty easy topic once we establish what a basis is. So if W is a subspace of Rn with a basis W1, W2, up to WP with P vectors, then W is of dimension P. So it just basically means that the dimension is the minimal number of vectors needed to describe the set. So if I can describe the set with one vector, it's one dimensional. If I can describe it, but I need 20 vectors, then it's 20 dimensional. Okay, and then very closely related are the nullity and the rank. So the nullity is just the dimension of the null space. And the rank is the dimension of the range. And conveniently, the nullity, so if we have an n by n matrix, so if A is an m by n matrix, then the nullity of A plus the rank of A is going to equal n. So if you have a question and it says find the nullity and the rank of a matrix, all you have to do is find one of these and you'll know what the other is. If it says find the null space and the range, you have to work through both of them. But if it asks for the nullity and the rank, then all you have to do is find the null space. You'll know the dimension of the null space, and then you'll have the nullity, and you'll be able to easily calculate the rank. So you don't have to calculate the range to get the rank. All you have to do is do the null space, which is a much easier calculation. Okay, so let's do a few examples. So first, very basic. 5.3, so let's say S equals the set of U1, U2, U3. The first question is, can this be a basis for R2? And the answer is very clearly no. It can't be a basis for R2 because we have three vectors. So let's say those are 2D vectors. That means that we're going to have more columns than rows. And in any matrix where we have more columns than rows, we do our augmented matrix, that's always going to be linearly dependent. So we can see if it's linearly dependent, then it is not a basis because the definition of basis says must be linearly independent. So that's just a very quick example, just to show, once again, another attribute. Moving on to 3.5.15. So once again, we have a pretty simple equation. So we have that x1, x1 minus 2x2 plus x3 minus x4 equals 0. So this is the only equation we have, so we have to express the solution. So we can write that as x2 times 2, 1, 0, 0 plus x3 times negative 1, 0, 1, 0 plus x4. And if anybody doesn't understand how I'm doing this part, just speak up so we can go back over it, but I don't want anybody to be lost. And then x4 times 1, 0, 0, 1. Okay. And we can see that this solution, x1, can be written in terms of the other three vectors. So the basis for this set is the set of vectors 2, 1, 0, 0, negative 1, 0, 1, 0, and 1, 0, 0, 1. So that means the dimension of W is 3. That makes sense to everybody? George, are you talking about this right here? Okay. Yeah, I just, so I set x1 equal to 2x2 minus x3 plus x4. And then I set x2 equal to 1 to see what x1 would be. Set x3 equal to 1 to see what x1 was in terms of x3. And then just see what x1 is in terms of x4. Okay. All right, let's move on to another example. Look at on this. Yeah, okay. So let's look at 3.5.23. So if we have A equal to 1, 2, negative 1, negative 1, negative 1, 4, 3, 8, 3. And we want to know both the nullity and the rank of this matrix. So because of this relation, we know that the nullity plus the rank is going to equal 1, 2, 3. So the nullity plus the rank is going to equal 3. So all we have to do is find the null space, and we'll know what the nullity is, and then we can figure out the rank. So that's the method we're going to use to solve this. So let's look at our matrix. And let's first make that first column clean. So 2 minus 2 row 1, 0, 1, 2, 0. And the bottom row plus the top row is just going to be 0, 3, 6, 0. We can see that this third row is going to delete from the second row. So we can write it out as 0, 1, 2, 0, 0, 0, 0, 0. And the top row, if we do top row plus the second row, 0, 5, 0. Now we can see um, from this matrix, we are able to get both. We could get our spanning set for the matrix, and we can also get the null space. So for x1, x2, we can see that they're both dependent on x3. So x1 equals -5 x3, and x2 equals -2 x3. So that x equals x3 times -5, -2, 1. So the basis is going to be the set of -5, -2, 1. So it's just this basis is just one vector. So we know that the nullity A is going to be 1, and the rank of A is going to be 3 minus 1, which is going to equal 2. So we've calculated both our nullity and our rank, and we should be good to go. Okay, and then I'll do one more problem, and then I'll just open it up for any questions. If anybody wants to go back to previous material, or if anybody wants to go over anything we've gone over today. And then next Tuesday, I'll go over orthogonal bases and the Graham-Schmidt process, kind of depending on what's included in the lecture and what's going to be in the exam. Okay, so last problem we'll go over is 3.5.27a. So if we have the set of 1, 1, -2, -1, -2, 3, 1, 0, -1, and 2, -1, 0. So that's our span. So it says find a basis and determine the dimension of the basis. So to find a basis, I usually just use the method that I like. There are a few different methods you can use, but the method I like is just to do the null space, do the calculation as if we were finding the null space. And you will notice if you look at the answers in the book to these questions, some of them are different than the answers that I've come up with on these and that I will post up on the website. And that's because there is an infinite number of solutions for each of these spans. So there are infinitely many ways you could write the span of this set. And really, once we find out how many, what the dimension of the span is, all we have to do is find two vectors associated with the set that have that are linearly independent. Okay. So if we do this, get rid of the first row, we'll get 1, 0, 0. And what does that look like? So we subtracted that row. So we're going to have -1, -1, -3, 0. On the bottom, we're adding 2 times the first row. So we're going to have 0. We're going to have 1, 1, and 4. So now if we get rid of the, let's multiply the second row by -1, and then get rid of that column, we'll end up with 1, 0, 0, 0, 1, 0. It's going to be 1, 3, 0. On the bottom, we're adding, so it's adding the 2 rows. 0, 0, 1, 0. And on the top, we're subtracting. So -1 minus -1 is 0. 1 minus -1 is 2. And 2 minus -3 is 5. 0. And then we can see that we'll be able to get rid of the 3 and the 5 just using the 1. Once we do that, we'll be able to get rid of the once we do that, we'll determine that we have matrix sorry. So that'll be our final matrix. And we can see that the leading one is the only non-zero entry in each of these 3 columns. So it is in reduced echelon form. We also notice that we have one free variable. So if we rewrite the solution, we're going to get that x1 equals negative 2x3, x2 equals negative x3, and x4 equals just 0. So that our solution is going to be x, sorry. Oh shoot, I'm doing unnecessary. So that would be finding the null space. We don't have to find the null space, we're just finding the basis. So we're finding the basis of W. This is a free variable. These 3 are constrained. So we know from the method we used before, we can just take the first, second, and fourth vector. We can get the basis of W is going to be the set containing the vectors 1, 1, negative 2, negative 1, negative 2, 3. We're taking the first and second, and now we're going to take the fourth. That's 2, negative 1, 0. And if we wanted to, we could work it out, and we'd get that this vector is going to be a linear combination of the first and second vectors. And we can see that. So if we take 2 times the first vector and add the second vector, we're going to get 2 minus 1 is 1, 2 minus 2 is 0, and negative 4 plus 3 is negative 1. So this one's independent, so it does not need to be in the basis. So that's our basis. And then since we have 3 vectors, we know the dimension of W is going to be 3. And that's kind of the introduction to spanning sets, dimension, null space, or nullity, and rank, and the basis in general. So anybody have any questions? Full first page of notes. And as with the other lectures, I will be posting the recitation notes. So all the recitation notes are on LMS under the recitation tab. So if you do ever miss anything from the recitations, all of the videos from the recitations and all the recitation notes are on there. If you haven't been on LMS in a while, all of the homeworks up through 3.2, the first half of homework 5 are on the LMS as well. So I have pretty much everything to do with the recitations, and homeworks is up there for you. Anybody else have any questions? Okay, I'll stop the recording.